All right, welcome everyone. My name is Ryan Nugent, staff here at Cal Poly. I'd like to thank you all for joining our Constellations Live panel Q&A for the 2021 Developers Workshop. We're excited to have these panelists join us today and discuss their presentations. Before we would begin, though, we would like to thank our sponsors. It's with our sponsors and exhibitors that we're able to give you this CubeSat Developers Workshop free of charge. So for this session, we would like to highlight one of our gold sponsors, Blue Canyon Technologies. So I'd like to thank them. And then we have a short video for them. So if we could play that right now.
This is our home. One small speck suspended in an endless sea of stars. Human curiosity compelled us to explore it and drives us to understand it. That's what keeps Blue Canyon Technologies at the forefront of innovation. We're a dedicated team expanding the limits of science and defense, using end-to-end spacecraft solutions, industry-leading pointing accuracy, and the highest performing satellite components. Our systems span Earth orbits and are capable of reaching the deepest environments to propel us into the unknown, because the final frontier is only the beginning.
Again, I'd like to thank Blue Canyon for being a gold sponsor for our event. In the chat, you will find more information about their virtual exhibit and some of the side meetings they have throughout the rest of the week. I would highly suggest making some time to engage with them this week. With that being said, I would like to introduce the moderator for our panel. That is Dr. Pauline Four, who is the director of the Cal Poly CubeSat Lab and assistant professor in the Aerospace Engineering Department. Dr. Four has been developing and managing international small satellite projects for the last decade, putting an emphasis on applying systems engineering best practices to small satellite programs. Dr. Four, the floor is yours.
Thank you, Ryan, for the introduction. Welcome attendees to this panel, and thank you to the panelists for joining us today. First, a few information on how this panel will be run. I will start by introducing each of the panelists, and then the panelists will provide a 2-minute summary of their presentation. I will have a few questions for them, and once we have gone through the 4 panelists, the floor will be open for a question from the attendees. For the audience, you can see in the bottom of your screen, you should find a Q&A button that you can use to submit your questions. So please use that, and I will be monitoring that. When you submit your questions, make sure you specify one of the panelists you would like that question to be addressed to. All right, with all that said, I would like to start with Dr. Ramon Ferrús. Dr. Ferrús is an associate professor at the Universitat Politécnica de Catalunya, based in Barcelona, Spain. He is with the Mobile Communications Research Group and currently collaborating with Sateliot company for the design and development of a low-cost satellite direct access IoT solution for coverage extension of terrestrial mobile networks. So Dr. Ferrús, if you'd like to summarize your presentation in 2 minutes, please.
Okay, thank you for the introduction. Happy to be here. It's my first participation in the CubeSat Developers Workshop. So it's I'm coming from the mobile communications area, but now collaborating with Sateliot company that is developing a solution based on CubeSats for IoT services. Mainly the context of the proposal of the presentation that you have here is that there is an increasing growing demand for satellite IoT services. And here also a key point to cover this demand is to be able to find solutions where the same standards can be used for both, for the terrestrial access and the satellite access. So the same chipset, the same hardware, mainly with software adaptations, is able to talk both terrestrial towers and satellite platforms. This is seen as a key element in addition to being able to lower the connectivity cost through satellite. And this is where the potential constellation of CubeSats, low density CubeSats, scalable constellation comes in front of mega constellations, in front of other solutions, just low density constellations for delay tolerant IoT services. That is the scope of the Sateliot company. But of course, to provide this kind of services with CubeSats, there is important challenges to address. Link budgets are limited. The beam layout that has to be supported in the satellite is challenging in terms of the transmit power that you need, the type of antennas that you have to put there, the processing capabilities, computing capabilities that you need in the satellite, and all these aspects are being worked out to make reality this project in the near term. Thank you.
Thank you, Dr. Ferrús. So first quick question from me is, were you able to secure a mission to fly your proposed solution, or what are the plans for it? If you could describe a bit more about it.
Yeah, now indeed, there are several lines in the project. Now we have already flight a first satellite that it's just being used to make AQ recording test with the kind of narrowband IoT signals that are going to be used. In parallel, there is now the development of the payload that is going to support this capability, and the plan is to fly this payload next year. But we are still in, let's say, the protocol is not yet finalized at 3GPP level. It is still being standardized. We are participating in the standardization work, and the idea with this, with the next satellite, is to be able to do more advanced than IQ recording test during next year.
Well, that's great to hear. Thank you. As a somewhat of a follow-up question, if people wanted to fly your service, what are your overall requirements on the host satellites to be able to accommodate the IoT?
Okay. Overall requirements now, the target is a 6U satellite. Now the specific requirements on the payload, indeed the payload is intended to be fit in less than 1U envelope volume. Not all the requirements are yet closed. We are now in PDR phase of the project, so there are still some open issues, but also we are in talks now with some providers, platform providers, also to start the talks for the integration and flying of this payload. But 6U satellites, less than 1U volume, the main payload.
All right, great. Thank you very much. Our next panelist is Mr. Mohammad Mubashir Hussain, who is studying for a Master of Science degree in Electrical Engineering at the University of South Alabama. He is working as a graduate research assistant at the Applied Electromagnetics Research Laboratory here or there. Mr. Hussain, if you could provide a 2-minute summary on your presentation, please.
Hello everyone, I hope you all are doing well. My name is Mohammad Mubashir Hussain. I'm a second-year master's student at the University of South Alabama. Here I am presenting a circularly polarized X-band patch array antenna with corporate feeding for CubeSats, which we developed for a SwarmX National Science funded SwarmX project. And it's a swarm of 3 small satellites, which will look for the equatorial anomaly between 300 to 500 kilometer altitude. And we designed the antenna for X-band downlink communication. And this SwarmX project is a collaborative project with 6 universities led by University of Colorado Boulder. Dr. Scott Pello, professor, University of Colorado Boulder, is leading this project as principal investigator. And with this X-band downlink communication, our basic goal will be download the science data from the space from the space. And this communication system will also have UHF uplink and downlink communication. And the antenna we designed for this X-band downlink communication is 2x2 patch array antenna with and it's the technique we have used is corporate feeding, and it provides 13 dBi right-hand circular polarization gain. And the mission from the link budget analysis of the mission, we saw that we needed at least 11 dBi right-hand circular polarization gain. And also our target was to achieve at least 15 dB return loss performance within the targeted bandwidth, which is 8.475 gigahertz to 8.5 gigahertz. 8.45 gigahertz to 8.5 gigahertz, which we achieved. And for this, with this design, we achieved 20 dB return loss within this bandwidth. So, and the 3 dB beam width of this antenna is around 35 to 40 degrees.
Thank you, Mr. Rosen. So my first question to you is, in your presentation, you showed the analytical results on the performances of your antenna. And so I was wondering, what is your plan for testing after the manufacture of the antenna? If you could speak a bit about that, please.
After fabrication, we will test the antenna both standalone and also on the CubeSat, placing the antenna at the same space which we are planning to place on the CubeSat. So we will test the antenna gain measurements and the S parameters, axial ratio parameters, all in anechoic chamber, which will be done in University of Colorado Boulder. And I'm working at University of South Alabama. Here we have designed the antenna in finite element method-based simulation software HFSS. And after we designed, we delivered the design to the CU Boulder, and they are doing the fabrication and testing part.
Great, thank you. And my next question, not related to the first one, is you mentioned that there are 3 satellites in the SwarmX constellation. Could you speak a bit more on how these 3 satellites work together, probably like from a communication standpoint for the mission?
Yes, they will have around 0.5 kilometer to 1,000 kilometer intersatellite distances, and there will be UHF crosslink communication, which will operate at 450 megahertz, and the intersatellite communications link rate will be 2.4 kilohertz. And together they will use for downlink communication, they will use code division multiple access. And also they will have a GPS and global star communication system to know where the antenna, where the satellite position is.
Great, thank you very much for the additional information.
Yeah, thank you very much.
Sorry, we didn't mean to cut you. It started virtually. Our next panelist is Mr. Conor Brown, who is the Director of Sales Engineering for the Spire Global Federal Team. Mr. Brown has been in the space industry since 2014, spending the several years providing hosted payload and small satellite launch services to a diverse customer base prior to joining the Spire team in October of last year. So Mr. Brown, if you would please provide a summary, 2-minute summary on your presentation.
Yes, of course. Thank you so much for having me on this panel. It's a pleasure to participate in the CubeSat Developers Workshop. I remember my first one in 2014 out in San Luis Obispo. I sure wish I could be there this year. Dr. Ferrús, as beautiful as Spain is, I'm sure you'd love California as well. So let's hope next year we're gathering together in person. But this presentation, I'm pleased to be representing Spire for the first time at the Developers Workshop to talk a little bit about the experience we've had on orbit with radio frequency intersatellite links. It was a pleasure to put this presentation together in late March, early April as well, because we had just concluded some on-orbit demonstrations that we're able to highlight as part of this presentation. And for those that haven't had a chance to watch the video or flip through the slides, we speak to a bit of the rationale to as why we need these intersatellite links in our constellation of satellites to drive down our data latency. We talk about how as we grow our constellation, it is the single most impactful way to reduce data latency across collection for those denied areas where we simply can't practically bring the ground segment into view. And we talk about how a targeted approach of strategic ground station deployment along with intersatellite links throughout the constellation will enable us to reduce data latency for high priority time sensitive capture to levels we've never seen before. So that's some of the focus in the background, and then we highlight specifically the first two batches of radio frequency S-band intersatellite links we launched. So we've launched a total of 4 spacecraft to date with RF intersatellite links on a total of 3 launch vehicles. The first was excuse me, I just lost the lights here in my office. The first was last September on a Soyuz vehicle. We actually launched 2 spacecraft into a sun-synchronous orbit. And then since then, we've launched a satellite to the ISS and deployed from the International Space Station, as well as on the SpaceX Transporter-1 mission. And so we've talked about a little bit of the in-plane and cross-plane ISL communications we've been able to achieve on orbit, as well as talk a little bit about what we plan to do next, including optical intersatellite links.
Thank you, Mr. Byrne. So my first question will be, in the presentation, you mentioned that the latency, you were able to reduce it by up to 5 hours. So I was wondering, how does that compare to other similar service providers? If you could speak a bit more about it.
Sure, I should state that the latency overall is typically well below 5 hours for our data collection. It can range from a matter of minutes to a couple of hours, depending on the ground stations and the passes. Also, how we prioritize our data and our constellation management tools. We're looking to get the majority of our constellation latency below some core metrics. Specifically, 15 minutes is a threshold that enables a lot of our customer use cases for the data sets to be actionable. So getting that certain percentage below that 15-minute latency as we grow and increase our collections will be something that requires intersatellite links and that we'll be targeting for sure. What we looked at in some of those simulations in the presentation were evaluating the impact relative to the benchmark of today. And so it can be a little deceiving. It's not as, but it does quantify how intersatellite links versus more ground stations helps the problem. And what we show is that for designated areas of interest over, mass population areas or things along those lines, ground stations are extremely effective, but for remote areas like in the poles or over open ocean, the most impactful way to do that is to have a smart routing of the data on orbit to get the most timely downlink.
Thank you. And then my next question is kind of actually by accident. We did not coordinate beforehand, but ties into your last comments when you were doing the summaries. Could you expand on what is next and how you plan on tackling the optical communication aspect for your intersatellite link systems?
Sure, a little bit. I'll certainly share what I can. And so, at Spire, we like to talk about what we've done. And so next year, I have a feeling we'll have lots to talk about when it comes to the optical intersatellite links. But what I can share is that we have an initial demonstration mission with 2 optical intersatellite link spacecraft planned to launch this year, quite soon, actually. And with that, we will take a similar approach to what we took with our radio frequency intersatellite link demonstration missions, where the second batch will be more capable with more stringent test conditions. And so that obviously offers much higher data rates and requires some things like precision pointing capabilities that our satellites haven't had in the past. So it's been a really nice way for us to mature our spacecraft roadmap and design, both to offer to space services customers that want to fly their software or payloads on our bus, but also for our own needs as we plan our next phases for our constellation.
Thank you. A new fun problem to solve.
Absolutely. It's keeping the engineers very busy. And I just want to add, I'm representing a very deep technical team, and I'm pleased that they're allowing me to do that. But that's why I put many of their names, I should say, on the first slide of my presentation. I do not want to take credit for all this tremendous work that they've done.
Yes. Thank you, Mr. Brown.
Welcome.
Our next panelist, is Dr. Steven Reising, who is a professor of electrical and computer engineering at Colorado State University. Dr. Reising has served as the PI of 6 NASA grants for technology development and demonstration of remote sensing of the Earth's atmosphere from CubeSats, including the temporal experiment for storms and tropical systems, TEMPEST demonstration, or I forgot the last part, I'm sorry. Or TEMPEST-D mission on orbit for more than 2 years and 9 months to date. So Dr. Reising, if you'd please to provide a 2-minute summary on your presentation, please.
Thank you very much for the very kind introduction, Dr. Farr. Recently, there is a realization of the capabilities of CubeSats and smallsats in constellations to benefit weather forecasting and to provide particularly higher temporal resolution, higher revisit time for forecasts. So we're not talking about the geostationary satellites, of course, that give you visible and infrared images that tell you where the tops of the clouds are, but we're talking about microwave signals that penetrate deep into the clouds and look at the interior, where the precipitation forms, where the ice crystals are, and can characterize much more about the storm. And so what we have demonstrated with the TEMPEST-D mission, as mentioned in the introduction, is for the past 2 years and 9 months, we've been on orbit, not only measuring individual storms, hurricanes, tropical cyclones, typhoons, but also global data. And so we have a treasure trove of data that's publicly available. And this is the first multi-frequency global data set that is available from microwave radiometers on CubeSats. And so it's been compared with the operational satellites, which are 20 times as larger and many times more expensive, of course, to produce and to deploy into space and operate. So, our instrument compares very favorably. The instrument is built at Jet Propulsion Laboratory. I've been collaborating with them on technology development, or Colorado State University has, and I've been leading as PI since 2009. So it's a long time of development, and this is a 6U CubeSat TEMPEST-D that was built in 2017, launched in 2018, and is still operational. So we then did a study funded by NOAA to look at the benefits of launching a constellation of something like 10 CubeSats. And it turns out that we can dramatically improve the temporal resolution of such observations. I'll stop there.
Thank you, Dr. Reising. My first question, because TEMPEST-D was only, so to speak, one satellite, 1/6U. So as you're expanding toward more satellites, do you plan on including those intersatellite link capabilities to improve the performance for either weather forecasting or maybe other aspects?
Well, that would be great if we can fit it on the platform and implement it. Yeah, it would be great to use optical communication, communication and getting our data to the ground. In fact, data latency are issues for us as well. And so I mentioned that it was built in 2017. We used the Cadet U radio, which is limited in terms of the number of ground stations since the technology has changed since then. So that's really important challenge to overcome. Thank you.
Thank you. And then the next question will be, could you speak more about the TEMPEST-9 status? If there any flying opportunity, will you plan maybe to include other payloads for other observations, or if it's solely for similar observation as was done for TEMPEST-D?
Yes, well, the TEMPEST-9 is again based on a NOAA-funded study. And so the next steps going ahead, also the NOAA chief scientist and the UMETSAT chief scientist in Europe, working with ESA, have been, saying good things about these satellites, that it's encouraging that what we've achieved with TEMPEST-D. And so we were on American Meteorological Society meeting in January on that virtual meeting. And so, but it's up to them about the funding and so what the decisions are made. We just showed NOAA that the industry providers are there to build both the microwave instruments and the spacecraft and launch the spacecraft and so on. So the industry providers are ready, and NOAA is looking at the possibility of a number of types of instruments, not only passive microwave, but also like hyperspectral or infrared and GNSS reflections. So they're looking at a number of possibilities, and I can't speak for exactly what they're going to settle on. Thanks.
That makes sense. Thank you for the clarifications. All right, so that concludes our overall introduction for this panel on constellations. And now I would like to open the floor for the audience questions. And at the moment, it doesn't seem we have questions. So I'm going to go ahead, and I prepared a few general questions for all the panelists, since we have a wide array of expertise and application. And one of the concerns that comes when we talk about constellation is maybe how do you, if you have any like tips and tricks almost on, especially maybe the assembly, integration, and testing part of, like, if things get easier, or if you have any overall like lessons learned from developing a constellation versus developing a single satellite. So I open the floor to either of you to address that if you'd like.
So I can speak for Spire, who obviously has, over the last several years, developed its own vertically integrated manufacturing facility. We've found that, plug and play isn't always, the best way, or isn't always a reasonable way to approach the problem. So we've brought more and more of our subsystems and capabilities in-house to maintain a vertically integrated manufacturing, test, and assembly line, and that includes our own test facilities. That's the benefit of being a constellation. I certainly sympathize and empathize that not everyone has that, and that a lot of these universities and other teams are building their first satellite, and that's part of the educational experience. But certainly we've developed our own in-house tools and recently become certified across multiple different manufacturing standards. So that's sort of how we've come at it from a commercial perspective, constellation viewpoint.
Thank you for the commercial perspective. Are there any other perspective? Maybe it was not the right question to ask. I can accept that.
Oh, it's a good question. I just, don't have a lot of detailed information. I mean, the cost definitely goes down as you produce more and you learn lessons that you can use in the future. I think for us, a federal laboratory or a federally funded research and development center like Jet Propulsion Lab would only want to build so many, right? So, NOAA has a mandate from Congress to fund industry. That's why I mentioned industry before, but still, we've proposed through JPL to build, on the order of 6 or 8, at there. But once you get larger than that in quantity, and I'm talking about the payload here in this case, the microwave instrument, then you probably would move it to industry. And so there's a question then on the process of moving that knowledge to industry, and the training of the specific industry, if it's an affordable, things like that, kind of the maturity level of the company too, in terms of their background in their experience in producing such sensors, because some people will be very experienced but very expensive. So you get the whole range from a startup shop, literally in people's basements, to so. But it looks like there's some good questions that came up in the Q&A. Thanks.
Absolutely, yes. Well, thank you, Dr. Reising, for addressing it. So yeah, we have a few questions that came up in the Q&A. The first question might be maybe a bit more to Mr. Osen. What is your opinion on using optical interferometry as a more accurate way to measure distances between CubeSats?
I'm sorry, I don't have much idea about using this measurement. I'm working with the basically communication system at like antenna level system. So I don't have detailed information about it. I'm sorry.
All right, that's fair. Could Dr. Ferrús or Mr. Brown or Dr. Reising feel comfortable addressing optical interferometry, or would you like me to move on? Okay, I'm moving on. That's totally fair. So sorry, Arshia, we cannot answer your questions. All right, next question is for Mr. Brown. You spoke about hosted payloads. Are you looking to expand your network, to be used with satellites external to your constellation, like Globalstar? Also, what bands are you using for your ground station? Is it also S-band like your ISL?
Thanks for the question. So from a space services perspective, we're looking to expand our network of what payloads we fly and offer customers access to our satellite platform and infrastructure that we've built up, which includes ground stations and soon will include intersatellite links, not necessarily to expand to networks outside of Spire, but rather continue to grow our own capacity and capability, and then offer that as a service to our customers. And that could be deploying algorithms or software onto our high-performance computing systems, or actually hosting payloads, customer payloads on our satellites, integrating prior to launch. Lastly, there is sort of a third category that we call solutions in space, where we'll work with the payload developers or the PIs, and if it's aligned with our roadmap, actually do joint development efforts for satellites where the customer may not be specifically providing hardware. Now, from a communications perspective, our ground stations are in UHF for TT&C, as well as S-band for command and for uplink and downlink. We are expanding our network capabilities with X-band as well, and that's an ongoing effort into the future to launch more satellites with X-band downlink capability, and then strategically deploy that throughout the ground segment as well. So it's UHF, S, and X for communication.
Thank you. The next questions might be also more oriented toward Mr. Brown or Dr. Ferrús. The question is there a generalized formula or program that you give it latency requirements and it tells you the size constellation you need, assuming satellite to satellite data forwarding?
I can say something on this, mainly from the perspective of the design of an IoT service and the way that we are approaching it in our project. Here, the point is that really these kind of services, the latency requirement, let's say, as being an incipient market, latency requirement, and from here derive all the needs and the design of the constellation is quite, it's not a straightforward way. We are more on the opposite way, in the sense that the approach followed is that mainly being able to provide service with a single satellite. Single satellite should be sufficient to provide service. Of course, then you need the scalability of the solution, and the point is that adding more satellites, and adding more ground stations, you progressively reduce and can give better latencies and this enables more demanding applications in terms of latency. But here the approach is that let's start this kind of services, let's foster this delay tolerant, because there are many applications that they don't need they can be quite soft in latency. You only need to, for instance, to check a sensor data 2 times a day. No, not relevant if the data is delivered 2 hours after it was captured. And this enables many applications, and from here you can grow and progressively reduce the latency down.
Thank you very much, Dr. Ferrús.
I would just add that it's an extremely complicated problem, and so there's a lot of modeling tools, and I know some of them are open source, some are out there. We have a few engineers dedicated to running different simulations where it's easier if you were to start from scratch, but that's not how we build a commercial constellation. Sometimes you take the advantage of the launches that are available. I'm optimistic that the launch industry will have more and more options, and so there can be a bit more smart constellation design for some of these small satellite companies. But a lot of times you have to work with sort of unideal orbital conditions and things like that. And to slowly build up constellation capacity through intersatellite links, we're trying to design a system that has the most flexibility, that can handle large crossing velocities, cross-plane communications, that sort of thing. But so, yeah, I think there's a whole science behind the orbital simulations and the constellation modeling that goes into this that I wouldn't pretend to say there's a simple tool for that.
Thank you, Mr. Brown. Mr. Brown, since you have the mic, the next question is for you. The RF ISL tests shown in the presentation were cross-plane. Have you also tested in-plane, and how was the performance?
Yeah, so we did do in-plane testing, and the idea was to accomplish that with the first batch of satellites, which launched on the same launch vehicle on the Soyuz sun-synchronous orbit. I decided to highlight some of the most stringent test conditions we had done. So that example where I included a latency reduction of 5 hours was just a random example, and the largest. There were several that showed a latency reduction of half an hour or 20 minutes or something much less than that. But that was the most extreme trial to date, just to sort of highlight the utility of that. Same goes with the cross-plane versus in-plane. I decided to look at a cross-plane demonstration that had the maximum distance achieved. So I think it was just over 4,300 kilometers range where we maintained the link budget and were able to close the link and transmit at the rate described in the presentation. But yes, we have done a number of in-plane trials, and we're continuing to do more and more trials every day. One of the challenges is documenting all of this and keeping up to date with the community. So this was an excellent opportunity to capture some of these results and share them.
Thank you. Our next question is addressed to all panelists, and it asks, are panelists aware of satellite missions planning to use any of the space-based broadband CubeSat constellations to interlink data and operation from scientific satellites rather than employing their own intersatellite comlinks, for example? If anybody would like to address that point. We should have a little music because you do not want me to sing. I guess the overall question is, instead of developing our own platform, are there ways where we kind of piggyback on other constellations that are being developed? And have any of you maybe considered that for your applications? And if so, why? And if not, maybe why?
Well, I don't know if the weather forecasting data that I'm talking about, it kind of leads into the question that was targeted for me, in that we're not doing nowcasting. We're more looking at the global weather forecasting. I mean, we're interested in rapid intensification of tropical cyclones and so on, but we're not talking about the 1 minute type of latency. We're interested, if we get 15-minute latency, that's 10 to 15-minute latency. That's enough for us.
Thank you. As I have you on the mic, would you like to address the question more addressed to you regarding the cloud analysis?
Yes, so the question asks about the modulation of cell phone signals by, it says water vapor. Probably more would be the scattering in the clouds, in ice clouds and so on. You know, probably be more sensitive to clouds and precipitation than water vapor. I think this is a good question for nowcasting, and you know, it's I don't want to speculate on the exact value of the technique, but I think that there's scientific potential to do that. That's really addressing a little bit different problem, a little bit different scale, spatial temporal scale than we are for our weather observations, because we're not drilling down to the individual you know, part of the city where it's raining. But that's a very good question to address, and very useful for weather providers.
Thank you, Dr. Reising. One more for Mr. Brown. Are you designing your optical intersatellite link terminals to be interoperable/compatible with standards such as CCSDS or SDA?
I can't speak to the specific standards, at least not without checking with my engineers, but the intent is to be interoperable and have some interoperability with these systems as a foundation. Again, remembering that we're looking to deploy a technology demonstration, and that capabilities can be enhanced and scaled for things like interoperability down the line. Good question, though. Thank you.
Thank you. As we are closing short on the time, I would like to provide a last opportunity for a panelist, maybe to say something that were not addressed in the question or in the conversation that you would like to communicate to the audience. So I'm going to go through another round. Mr. Hossein, if you'd like to get us started.
Thank you all. And as I have already mentioned, I'm working at the University of South Alabama and National Science Foundation's SwarmX project. And if you have any questions about our project or our work, you can feel free to email me or one of our like co-authors, which are Dr. Scott Pello, Dr. Saeed Latif, and one of our team member, Brody Wallace. And thank you all for being here.
Thank you, Mr. Hossein. Dr. Ferrús?
Yes, so I think that it is quite important to see also this opportunity of using CubeSats, nanosatellites, for the delivery of these services that are expected to have a significant increase in the next year through the hand of the adopted protocols in terrestrial networks, narrowband IoT, LTE-M. Now there is a strong support from the industry also to adapt the same protocols to the space. And for sure here there are many different solutions with big satellites, mega constellations, but also there is opportunity for nanosatellites, CubeSats to provide good solutions to specific services at cost-effective prices. So, and this is not empty of challenges. The design of the CubeSat deserve also to be closely analyzed. Thank you.
Thank you, Dr. Ferrús. Dr. Reising?
Thank you, Dr. Ferrús. I think that there is definitely great potential to improve weather forecasting given CubeSat and small sat constellations. At much lower costs, and to make observations more frequently. And these need to be on a global basis, so they're not limited to where people have cell phones, because a lot of the, just a small comment, a lot of the observations are, the storms are coming off the coast, and the fronts, as you know, are happening worldwide. And so they're more and more challenged with climate change to improve forecasts and to improve the lives of people. around the world. And I think we can do this with microwave sensors on CubeSats and as in collaboration and partnership with other sensors. So thank you very much for this opportunity.
Thank you, Dr. Reising. And Mr. Brown.
Yeah, thank you so much. And I'll echo Dr. Reising's comment is, you know, today I focus very much on the infrastructure and the constellation of Spire. We haven't talked much about Spire's data collection, but that's okay. We can save that for the next one. I probably talked enough on this panel. But I do just want to say this sort of presentation and interaction with industry is what I've missed recently with COVID and the restrictions. So I really thank you for bringing us together. I encourage those in the panel. I see almost 70, 80 plus attendees to reach out if there's ways we can collaborate. There's hosted payload volume available on Spire satellites launching if there's ways our technologies align, or if we can marry data sets on the ground to come up with better weather forecasting or more comprehensive ship tracking. Please reach out. We're always looking to work with others in the industry, educational, commercial, or government.
Well, thank you, Mr. Oh.
Well, thank you. It was a pleasure.
Thank you, Mr. Brown. Thank you to all panelists. Thank you to all the attendees. That concludes our panels on Constellation. Come to the next panel on trains, databases, and standards. That will be another exciting moment for us. But thank you all. Have a good rest of your day.